Hello, friends. So in this video today, I'll explain linear regression. So linear regression is a very fundamental and basic topic, especially if you're studying machine learning and data science. And in this video, I'll try to explain some of the basics of this topic, and hopefully you'll have a better understanding too. All right, so let's get started. So suppose you have a data set of living area size and monthly rent of the apartment in your city, which looks something like this. So on the left-hand side, you have the living area. Right-hand side, you have the prices. And if you try to plot it on the x-axis, the living area in square feet versus on the y-axis, the price, it might look something like this. And you might ask the question that, well, from this data set, how do I learn to predict the monthly rent of an apartment given a living area size? So first thing that you can observe is that the outputs are scalar values, which are essentially the monthly rents. And so the prediction that you're trying to do is essentially a regression problem and not a classification problem, because our output is a scalar and not one of the different class levels. So essentially, we want to learn a function f that goes from x to y, where x is the space of all possible living areas of an apartment, and y is the space of all possible rents, which best describes our data. So suppose you're given a finite data set, training data set, which is kind of an input-output pair, x1, y1, x2, y2, etc. So in general, x is called the features or the covariate. So the example that we have provided, we have only one single feature or covariate, which is a living area size. But you can clearly understand that you can extend this problem to have multiple different covariates. For example, you may have the number of bedrooms, number of bathrooms, etc. That describes each of these apartments. And then you have this associated output value, which is the corresponding rent, and so on. So in general, we'll try to formalize this as follows. So we'll represent x by all the possible covariates or features, and y is always the scalar. And the relation between x and y that we hope to learn is a linear model, and that's how the linear term comes in the linear regression model. So this relationship between x and y can be modeled through a noise term or an error variable epsilon I. So essentially, for the ith data point in your training set, yi, you can represent that as a linear term, which is essentially a linear combination of all the features for the data point xi. Along with that, also you have an epsilon I, which is an error, unobserved error, which is typically a Gaussian distribution or a normal distribution with mean 0. So, 0 mean, and you have the variance is 1 over sigma for some sigma, which is a scalar value. So once we have defined our model in this way, what can we hope to learn from such model, right? So the first thing that you observe is that since these noise terms, epsilon i's are unobserved, the best you can hope to learn is a parameter vector w hat, let's say, which is w hat 1, w hat 2, all the way up to w hat t, that minimizes the sum of the errors between the yi, that is the true output, and the linear combination of the features given this parameter vector. So essentially, the parameter vector w hat that you try to learn is that over all possible linear combinations of the different features, the w that minimizes the error between this prediction, which is a linear combination of the feature, and the true output level measured in some appropriate way. So what can be a good way of measuring errors? So, well, typically we can use something called a squared error as a natural choice of error function. And later we'll see that this choice is not by arbitrary choice, but it has some other sort of meaningful kind of justification as well. All right. So if you first look at the ith data point, basically we're talking about. Let me see if I can. Oops, sorry. Let me see if we can choose my pen over here. Oops, sorry. That's back. Okay. So if we. So if you look at the ith data point, so essentially we are talking about this term. So this is your true output level for the ith data point. And this term is basically a linear combination of all the different features, D features, based on certain value of W. So this difference is nothing but the squared difference between your actual output for the ith data point and your prediction, which is some combination of the features based on the W. And then if you sum over all possible n data points that you have in your training set, then this will be nothing but the sum square error. And what we want to minimize that since x and y's are fixed given your training data set, it's a function of W, and we want to minimize over all possible W's such that it minimizes. So now you can represent this second term over here. So basically this term in the kind of in a matrix vector kind of representation. So this is nothing but the dot product between the ith data point and the W. So now it becomes a little bit much cleaner representation. And you are basically representing that or trying to find a W that minimizes this square. So oftentimes you'll also see that this term called mean square error, which is used in terms of linear regression, see that instead of using the sum square error, you could have also taken the average. So this is basically sum over all n number of data points. So if you simply divide that by n, that will give you the average mean square error, average square error, which is typically termed as mean square error. But since we are trying to minimize our W, so this 1 over n simply acts as a scaling factor. So whether you have multiplied this square error by 1 over n or not, it does not change the W, which minimizes this quantity. Right? So often we'll use this squared error as opposed to mean squared error, sum squared error as opposed to average sum squared error, because it gives essentially the same result, but it's a little bit easier to kind of work with, especially when you take different derivatives and so on. Anyway, so let's remove some of these. Sorry, okay, let's remove some of these. Okay, so far so good. All right, so let's go to. All right. So now suppose we use the following compact notation that we represent each of our training data point in the form of a matrix. So the first row of this matrix basically represent the first data point. And so each of the columns corresponds to different covariance value. So this phi then is often termed as a design matrix, which is n times t matrix. So it has capital N number of training rows, which is one row corresponding to each of the training data. D is the number of features or covariates, and Y is essentially the output levels for each of those n data points. And then we seek to find a W such that phi I times W is going to be exactly equal to Y. So now bear in mind that we will not find this exact solution that that phi times W is exactly Y, because we have this unobserved sort of noise terms in our linear model. So the linear regression essentially translates finding W hat in such a way that we want to basically represent this quantity in the form of a even much cleaner representation where this sum square error. So if you look at this term now, so each of these terms, okay, so let me again get my pen back. So if you look at this term over here, this is simply the square error for the ith term. You are summing over n number of data points that you have in your data set, and this whole quantity again can be compactly represented as in the form of a y minus phi w, and this is basically the square norm of this vector. So essentially, if you look at this term is nothing but a matrix vector multiplication, which will have a size of, remember, phi has a size of, this matrix has a size of n times t, and this W has a size of d times 1. So this resulting, this vector is going to have a size n cross 1. And each of these entries of this term corresponds to your predicted value based on when the linear set of coefficients are W, right? And correspondingly, you also have a y, which is also a n cross 1 vector, which is the true level. So essentially, when you are taking this inner product, square of this, the norm, essentially you are taking the square of, this quantity. matrices. And so this is exactly same quantity as here, but you are kind of representing in a nice compact kind of way. Okay, so let's see this. And move on to the next slide. Okay. So we can actually get a closed form solution for W hat in case of linear regression. So essentially, remember, you are trying to minimize this quantity, which is a squared norm. So the squared norm, you can simply write in the form of a dot product. So it's y minus phi W transpose y minus phi W. And if you take, distributed terms, there'll be 4 terms, y transpose y minus 2 times, W transpose phi transpose y. And plus W transpose phi transpose phi and W. Okay. So now to find W that minimizes this above sum square error as a function of W, we can simply take the derivative of S of W with respect to W and set it to 0 and solve for W. Right? So the first question is that, well, but it involves derivatives. How do you find derivatives that involves vectors and matrices? Well, it turns out that it's kind of very, very similar to how you deal with scalar values. So in case of scalar value derivatives, so let's say you have a function f of x, which is some constant term p of x. In case of scalar derivative, the answer is b. If it's x squared, it's 2 times x. It is b times x squared is 2 times b times x. The vector derivatives is kind of similar. Only thing is that you have to be a little careful about the sizes of vectors or matrices. So if you have a vector x, which is multiplied with a matrix B. So capital letters typically represent matrix, and the small letters typically represents vector. So essentially, you have a column vector X that you are taking transpose with, so it becomes a row vector. You're multiplying that with B, and if you take the derivative, if that is a function, if you're taking the derivative with respect to X, the result will be P. Same way, if P is not a matrix but a vector, then the result will be just a vector. If you have X transpose with itself, X transpose X is your f of X, then if you take the derivative with respect to X, the answer will be 2 times X. And if you have a kind of quadratic form that X transpose some matrix B times X and take the derivative with respect to X, then the result will be 2 times Bx. Right? And B is a vector and X is a, B is a matrix and X is a vector. So it's kind of very, very similar to the scalar derivatives. The only thing is that you have to be a little careful about the matrices and vectors. So now once you know how to take the derivatives with involving vectors and matrices, now we can simply take the derivative of S of W with respect to W. So the first term over here, y transpose y, is it's constant because it does not have any vector, the term W. Second term, we have to take the derivative with respect to W, we'll have minus 2 times phi transpose y, and the last term over here is the quadratic term. Again, if you take the derivative with respect to W, we'll have 2 times phi transpose phi, W hat is equal to 0. And so you are taking the derivative W and set W to W hat. And then if you set it to 0, if you change side and take the inverse, essentially you'll have a solution which is W hat is equal to phi transpose phi, inverse of that times phi transpose y. So this quantity over here, so if you, look at this quantity over here, so this is typically known as pseudo inverse or Moore-Penrose pseudo inverse. So we have this now closed form solution for linear regression problems, which is kind of a very nice thing. But we'll try to explain some of the issues associated with, and also explaining the same closed form solution from different sort of perspective as well. All right. So now that you know that linear regression has a closed form solution, what can you do with it? So there's still a couple of unresolved issues with this model. For example, you might ask, what is the probabilistic interpretation of linear least square linear regression? The reason why I need a probabilistic interpretation is that, remember, when we define our model, linear model, we have an noise term. Each of the noise term has a probabilistic distribution, which is nothing but a Gaussian distribution with 0 mean. So it's kind of a fair question to ask, What is the probabilistic representation? Because a linear model has some probabilistic term associated with it. So next you can ask that, well, in what ways you can generalize this design matrix phi, if at all you can generalize. The other thing is that, remember, in the closed form solution, you have to take the inverse of this matrix phi transpose phi. So what happens if this matrix phi transpose phi is singular? That means it has, its eigenvalues, at least one of the eigenvalues is 0, meaning that you cannot invert it. How do you find a solution in that case? What is the geometric interpretation of this solution, linear regression solution? And so for the model that you have assumed is that the linear model actually passes through the origin, right? So what happens if it doesn't pass through the origin? You have to provide some kind of offset, but how does that offset changes your solution, the closed form solution? So we'll try to deal with each of these issues in a little bit. So the first thing is this probabilistic interpretation. So remember our linear regression model, the input-output relationship we described at the beginning is that you have a linear model which is given by X transpose W, that is a linear combination of all the features, plus you have this epsilon, which is this error term. So this epsilon follows a Gaussian distribution with mean 0 and a variance, which is kind of 1 over sigma. Right? So typically we define the inverse of the variance to be a precision. So now it's a very statistics 101 is that X transpose, so epsilon, if it is a normal distribution in 0 mean, and if you add something to the normal distribution with mean 0, then your mean just gets shifted and your variance still remains the same. So that means once the Y, since you are adding a quantity, which is this quantity, which is a scalar quantity, then your this normal distribution simply gets shifted in such a way that your variance still remains the same, but your mean now, instead of being 0, it becomes X transpose W. So the mean is shifted by exactly the same scalar. So now, so this is a normal distribution with mean X transpose W and variance 1 over sigma. So normal is a multivariate. Normal distribution is a univariate normal distribution, and it has a common, PDF formula for that. If you apply, so for mean with mu and variance sigma square, the PDF of that is simply 1 over square root of 2 pi sigma e to the minus x minus mu whole square divided by 2 sigma square. So in our cases, the variance is in 1 over sigma, it's not squared, etc. So if you plug in the exact same formula over here, you have the probability density given a data point, given a W, given a sigma. The probability Y varies according to this, normal distribution and a Gaussian distribution, whose PDF can be given by, this formula. Simply, plugging in appropriate mu and sigma in this, standard normal distribution PDF formula. So the first observation that you make is that for a normal distribution, its mean value is given by X transpose W. That is because this is a normal distribution, it means X transpose W. So that means the conditional expectation given a fixed X, the Y value, its expected value is nothing but the mean of this distribution, which is X transpose W. All right, so with that understanding, so let's move on to the next slide. Okay. So now, if you are given a n pairs of input-output data in your training set, x1, y1, x2, y2, all the way up to xn, yn, and we can try to find the likelihood of seeing the different output levels given the actual data points along with this, a particular coefficients vector w and sigma. Then we can write this joint distribution in the form of a product of individual distribution, because we have assumed that all these individual input-output pairs are IIT. So the joint distribution, we can simply factor it as a product of individual probability densities because of these IIT assumptions or independent assumption. So now, so once you multiply each of these probabilities or PDF values, so each PDF value is a value in between 0 and 1. So multiplying a bunch of n numbers which are very in between 0 and 1 is kind of a little bit difficult to deal with. So often you can take a logarithm, because the logarithm of product is becomes simply sum of the logarithms. So then once you apply this likelihood, log likelihood, then simply you can write a sum of log of this individual probability densities for each of these endpoints. And we have explicit representation for each of these density points, each of these PDFs. So now if you plug in that value and take the logarithm, then you can kind of simplify these things involving three terms. One is n over 2 log sigma minus n over 2 log of 2 pi minus sigma over 2 sum over I equal to 1 to n yi minus xi transpose w whole square. So if this is your if you're just starting with machine learning and data science, I'll definitely encourage to do this derivation. It's extremely easy, just few lines of derivation, but it kind of will help you to understand how you kind of derive from this PDF representation of each of these of this normal distribution and taking the logarithm how and taking the sum, how it kind of end up in this kind of representation. So we can now represent this in the more closed form way, where the first term, second term remains as it is, but the third term we can simply write in this matrix vector kind of compact representation, which is a square norm of y minus phi times w. All right, so now let's call this equation 1, and essentially we want to maximize the log likelihood. That is, we want to find the maximize the probability that given these data points and w and sigma, how we want to maximize the probability of seeing the corresponding true levels. Now, if you look at over here, maximizing this is same as minimizing the last term if you fix for a particular value of fixed value of w. Right? So that is the first observation that we'll see, that for any fixed w, to maximize equation 1, we essentially need to minimize this sum square error. So now see that this is exactly the same quantity that we're minimizing, where we started with our sum squared error when you started talking about this linear regression in the first place. So a choice of error function, that is how we are measuring the true level versus the predicted level, was not by coincidence, or it was basically comes from the very fact that if we look at this probabilistic interpretation, then this automatically gives rise to this sum square error or average sum square error kind of representation as a measure, good measure for a good kind of metric to measure the difference between the actual levels and the predicted levels. Now, suppose this W sub ML, which is the maximum likelihood kind of estimates, be the choice of W that maximizes the log likelihood of this equation 1. Now, if you take again the same way, take the derivative, set it to 0 and solve for it, you'll see that the solution of this WML is exactly the same as the solution, closed form solution that we received at the beginning of the lecture. So this is the exact same expression of optimal W hat that we have seen before. So similarly, now if you take derivative with respect to sigma, and let sigma sub ml be the value of the sigma that maximizes the log likelihood in equation 1. So take the derivative with respect to 0, set it to 0, etc. And then you'll see that, again, another kind of expression that you can see, which is 1 over sigma ml is equal to 1 over n, sum of these terms, which is, again, kind of predicted value, actual value, minus this predicted value based on this, this WML as the coefficients for this linear combination. So the inverse of noise precision here is same as the variance of the target value around the regression function, because again, remember, this is kind of the mean value whenever your W is set to be W sub ML. And this quantity is nothing but we are measuring how far the actual prediction is from the mean value. So this is nothing but kind of the variance. So the inverse of the noise precision is nothing but the variance of the target value around this regression function given by your maximum likely solution. All right, so the next topic that we're going to talk about is that the design matrix that we have seen so far can be expressed in a more general form. So instead of having the design matrix, we can represent as kind of, phi of, so it can be a n times m matrix. Again, each row corresponds to a data point. And our general matrix, now instead of having d columns, unlike d columns, we can have m number of columns. And then each column basically represents a different kind of function. So ith column represents phi I. So the first column is phi 1, second column is phi 2, etc. So the first row that corresponds to that, what happens if the first data point, the different values are going to be, if phi 1 is computed on the first data point, phi 1, if phi 2 is computed on the first data point, and it's the same way phi m is computed on the first data point, that will give us the first row, right? And so on. So here, phi I for I to m is a function that goes from Rd to R. So that means it takes a data point and gives a scalar value, typically which is called a basis function. So we can kind of, concatenate all these basis functions together and represent in the form of a vector. So in case of linear regression that we have seen before, phi of I for any given data point x is simply the ith coordinate of x, so which is kind of the ith feature. So we can simply say that for any j, that is xj is the jth data point in your training set. And if you look at the phi I of xj, that is nothing but the ith feature or the ith coordinate of the jth data point, right? So, and m is of course d, because each data point has d features that you have seen before. So the ith column of phi is nothing but the function fi evaluated at each and every single data point x1 to xn in your data, in your training set. Okay. So in general, the ith column of design matrix phi can be described by a function phi I. So the function phi I can be nonlinear. It can have different choices, whatever way you like. It can be polynomial function, right? So for example, phi j of x could be some polynomial of the jth coordinate or the jth feature or the jth covariate of x. It could be Gaussian function with certain mean values and standard deviation, which also you can think about the location and scale parameter. It can be a sigmoidal function, and so on. So even though each of these phi i's can be nonlinear, we are still seeking a linear combination of these nonlinear functions that best describes your kind of variable. So even though it's a linear combination of nonlinear basis function, because individual basis functions are nonlinear, essentially what you get is a nonlinear function, right? All right, so for any xy, we are seeking still a vector w. So now this w will have m components, capital M components, because you have m number of basis function, and it is simply a linear combination of all these m different basis functions. So this coefficient will tell you how to combine all these different basis functions given any x, so as to predict its true output y. All right. So now, so suppose the design matrix phi, which is n times n matrix, is constructed using m basis function and using n input-output pairs. So it's basically your training set. So any matrix, can be decomposed as a product of three different matrices. So the reason that we are going to into this route is that now we have kind of a free variable capital M. We can choose, the different number of the different number of basis functions, which can be different than the number of features you can have. And that will have some effect that how we can take the inverse of this, matrix, phi transpose phi. And that is something that we are going to study next from the point of view or the lens of singular value decomposition. So any matrix that can be decomposed as a product of three matrices. So typically, this is called a matrix factorization, typically known as a singular value decomposition. So let the singular value decomposition of any matrix phi be U times sigma times V transpose. So typically in this representation, U is an n by n unitary matrix. So that means if you take U transpose U or U transpose, that will give rise to an n by n identity matrix. The sigma is an n by n diagonal matrix of singular values, where you can have at most r singular values which are positive. Everything, all the other singular values are 0. in which case the rank is R. And then you have V is M by M unitary matrix again, such that V transpose V, or if you take V times V transpose, it becomes M by M identity matrix again. So how does this least square linear regression solution look in terms of this, this U, V, and W? Let's try to work that out. It's actually quite simple. So we know that the closed form solution has this particular form, phi transpose phi, inverse phi transpose y. Now we can, using singular value representation, we can write this phi in terms of U sigma V transpose, and then we have these unitary representations. So let's try to work this out and see how it looks. So remember, phi is U sigma V transpose. So phi transpose of that will be U transpose of that. So V sigma U transpose. So similarly, if you plug that in, U transpose U is simply identity matrix. So you end up with this, and then this, since phi is a diagonal matrix, phi times phi is the square of the diagonal matrix. So that means each of the diagonal entry becomes simply squared. And then if you have to take the inverse of this, then we have the inverse of V is simply V transpose, and the inverse of a diagonal matrix is simply if the entry is non-zero, then it simply becomes 1 over that diagonal entry. And if it is 0, then it's simply going to remain as 0. And we represent that in the form of phi plus, and then we're basically taking the inverse of that. So that means this representation phi plus is going to be the same value as sigma if it is non-zero, and it's 0 otherwise. And then you're basically taking, since you're taking inverse, you're basically dividing. So it's basically 1 over the diagonal entry. If the diagonal entry is non-zero, otherwise it's 0, and you are taking the square of that. Right. All right. So now, again, if you represent this one, take the inverse of this, the second term over here. So U sigma V transpose of that will be V sigma and U transpose, because a diagonal matrix, transpose of a diagonal matrix is same as before. So again, V transpose V is identity matrix. So then you are left with sigma over here, and you transpose, and then sigma plus to the -2 times sigma is nothing but sigma plus to the -1. And essentially that means this is simply, and remember, some of these eigenvalues, singular values, are non-zeros. And some of them are zeros. The ones which is 0, they do not contribute anything. So essentially, you can represent this in the form of a sum of all the non-zero singular values. So it's UI. So UI is basically the I throw off this unity matrix, and then UI transpose Y divided by the singular value times V of Y. So sigma plus is simply the pseudo inverse of this. So this is sigma plus is nothing but 1 over sigma I. If it is non-zero, otherwise it's simply becomes 0. So there are a couple of observations that we make from this representation. The first thing is that even if a singular value is small, then a slight perturbation of Y can lead to a very large kind of error. So the reason is that, so what basically it's saying is as follows. So suppose you have for one particular okay. So if this quantity is, so let's say one of these, so let's say phi 2 is very, very small and close to 0. So what that means is that 1 by sigma 2, so if sigma 2 is very close to 0, will be very large. Right? So then that means if you change your y just a little bit, then that might actually, because 1 over sigma is very large, just a mild change in y might drastically change your vector, coefficient vector w prime. And since you're making your prediction based on this, this coefficient vector, that means your linear regression solution can be, vary very, very drastically. Right? So this is kind of a problem that we'll see how to kind of deal with in a minute. Okay, let me first remove some of this thing. But remember this important point that even if a singular value is small, then a slight perturbation of y may lead to a very large error in the least square linear regression problem. Okay, so let's see. So there are two potential problems with linear regression that we have seen so far. One is that if the matrix phi does not have a full rank, then the least square linear regression does not have a closed form solution, simply because that phi transpose phi does not exist. Right? So in the sense that, well, I mean, it exists, but it's not a full rank matrix, so you cannot take the inverse. Second thing is that at least one of the singular values, even if it's kind of has a full rank, if at least one of the singular values of the design matrix is very, very small, then small perturbation of the output values will lead to a very large error in your solution. So a simple single trick to solve this problem is often to apply something called a regularization, which essentially try to solve this problem. Is that, remember, this part was our original problem that we are trying to solve in our original least square kind of representation. That is, this is nothing but the sum squared error. So this is nothing but the sum squared error that we are trying to initialize at the very beginning and give a closed form solution, which was exactly same as the maximum likelihood solution. But now we are saying that, well, let's try to solve a problem, slightly different problem, where we add this additional terms, which is lambda times, square of the norm of this vector W, and then this combined quantity we are trying to kind of minimize our W. So from the regularization perspective, you can think about there are two terms. So you can think about that this is kind of the sum squared error terms is often also called the data fitting term. So how well the model describes or fits your data. And this one basically known as regularization. So it kind of applies some sort of a smoothness of this, the solution. So essentially, this regularization parameter kind of controls that which of these two quantities will, control or influence the solution. So, very easy way think about that. If lambda is very, very high, right? So I'm just increasing this, upward row, meaning that lambda is very, very high. So that means in order to minimize this, and in order to minimize the effect of this, essentially we'll make sure that the norm of this, the second quantity, is actually very small. And when the second quantity is actually very small, essentially we're saying that, well, the norm of W should be kind of very small, right? So that means W is going to have a small norm. So on the other hand, when lambda is very, very small, then even though its norm can be very large, but combine the second term together is not going to influence that much. Then in order to influence the sum of these two terms, we essentially will make sure that the first term is as small as possible. So basically, you are trying to minimize the data fitting term as small as possible. That is, fit your data as well as possible at the expense of W, or norm of the W being very large. Right? So this lambda, this regularization parameter, kind of is a trade-off between how well you fit your term versus how large the norm of this the solution vector W could be. Okay. All right. So let's remove some of these. All right. So now. So the important thing is that even applying this regularization term, we'll see that we can still have a closed form solution applying the exact same kind of differentiation method that we have seen before. Okay. So let's see. So this lambda is typically known as regularization parameter. And it turns out that this problem is equivalent to the following minimization problem under constraint. That is, you're trying to minimize this data fitting term under the constraint that is the square norm is at most, some eta. So, so for appropriate choice of this parameter, we can always, so there is kind of a relation that each regression parameter gives rise to this term eta. So this is often called a constraint optimization because you want to minimize this data fitting term, which is the unconstrained version, under the constraint that the square norm can be at most eta. So these two techniques can be related using Lagrange's multiplier, which is kind of standard optimization technique, but probably a different topic of discussion. So now, again, if you look at this expression over here, again, take the derivative, set it to 0, you'll see that again you can get the exact, not exact, but this exact same way you can get a closed form solution. And the solution looks something like this. So it's now phi transpose phi plus alpha times I is an identity matrix inverse, and then we have this phi term. So if you look at the original solution and the solution that we have over here, only difference is that now this term, so this term is kind of the only addition. So it's exactly same as the closed form solution as before, this regularized solution, but now you have, this this additional diagonal matrix. So remember, this is an identity matrix, and this is lambda times this. So this matrix actually looks something like a diagonal matrix. So all the diagonal entries are lambda, etc. All the top diagonal entries are 0 that you are adding to this phi transpose phi. So now, so this actually makes sure that all the so once you add this, all the diagonal matrix of this phi transpose phi is being added by lambda. So now it becomes diagonal heavy, and that actually makes sure that you can actually invert this matrix. Right? That is the whole idea, or another way to interpret that why now you can take the appropriate inverse is simply because you are making this, phi transpose phi, which may not have all the singular values, or it may not have a full rank. That means not all the singular values are going to be positive. But the moment you add this, additional term to each of the diagonal element, essentially you are making all the singular values positive, and that means the matrix becomes non-singular, and now you can take a inverse of the matrix and compute this closed form sort of solution. Okay, so let's see. So I is M by M identity matrix. So for well-chosen lambda, the matrix is diagonally dominant, has an inverse, and each of the eigenvalues is at least lambda. Right? That is the kind of, by adding these quantities, you are making sure that each of the eigenvalues of this matrix, phi transpose phi plus lambda I, is at least lambda. So that means if original eigenvalues of this matrix, phi transpose phi, are 0, by adding this term, you're actually converting those eigenvalues to be 0 as lambda as well, making a singular matrix non-singular so that it can take inverse. Now, so there are different ways you can apply regularization. So the one thing that we have seen applying the regularization is the square kind of square norm of W, but you can also use the to the power of Q. So one common another very interesting regularization which is often used is when Q equal to 1. So your regularization terms now simply becomes the L1 norm, or sum of the absolute values of Wi. It turns out that if you try to minimize this, so now you do not have a closed form solution, but the solution that you observe essentially give you a kind of very sparse solution. So that means many of these entries of the solution WRS that you get are going to be 0, and only some of the entries are going to be non-zero. So essentially that means since we're taking a linear combination, this sparse solution will basically dictate that when you're taking a linear combination of all different features, only the features whose corresponding entries in this WRS are non-zero are the one whose linear combination best describes your data. So that means you may have, let's say, 100 different features, but if, let's say, the W vector has, I don't know, let's say only 30 terms are non-zero, then essentially your linear model will be dictated by the linear combination of those corresponding 30 features, and not the other 70 features maybe kind of redundant in explaining your model. So most of these coordinates of this WRS are zeros, and only few coordinates are non-zero, and then only the corresponding features or the basis function, the linear combination best describes your model. So this is typically known as L1 regularization. However, there is no closed form solution for this. So the reason that why it provides a sparse solution is an interesting question, and So we can try to explain that in the form. So the regularization terms, the contours kind of defines the different constraints, right? So think about, let me try to explain what you're trying to, what these two pictures are kind of depicting. So let's say you have only two features, right? Sorry. Okay. Okay. Oops, this is not one data. Okay, so let's say you have this one. All right. So let's say your W has only two coordinates, right? W1 plus W2. So W1 and W2 are the two different coordinates. And so what does, so let's say, what does this mean? So, this is nothing but W1 square plus W2 square equal to 1. So this is nothing but the equation of a circle, right? So now if you have, okay, so now if you have, so this is nothing but the equation of a circle. So basically it's saying that if this constraint is satisfied, then the constraint is nothing but a circle, something like this. So which is basically a square 2 norm. Now, if you have a L1 norm, which is, let's say, W 1 is equal to 1. So essentially, you're basically saying that, well, W1, absolute value of this, plus W2, absolute value of that, is equal to 1. Okay. Now, instead of it being equal, if you basically say this is less than or equal to, that is, it may be at most this, then you're basically saying that, well, this is, your solution should be somewhere inside this circle. So now, again, if you try to represent this, the linear term, then there are four possibilities, right? Depending on whether it can be positive or negative. So you'll have four sets of equation, W1 plus W2 equal to 1, W1 plus W2, or negative W1 plus W2 equal to 1, negative W1 minus negative W2 equal to 1, and then the other one will be W1 minus negative W2. So this will give rise to four different linear equation, which is given by these different lines in the left figure here. And then similarly, if you have this is less than or equal to, so that is the L1 norm is at most 1. So then each of these will be kind of, non-linearity, less than or equal to inequality. And this will now correspond to that. The solution, this constraint will say that, well, the W, and remember in this case, this is basically the W1 coordinate, and this is basically the W2 coordinate. Same as here, this is the W1 coordinate, and this is the W2 coordinate. So in the parameter space, by saying that, your square 2 norm is at most 1, you're basically saying that, well, your W must better be within this, in the parameter space, within this circle of radius 1. And whenever you're saying that, well, my L1 norm is at most 1, then you're basically saying that W in this parameter space should be within in this kind of rhombus area, where each of these quantities are nothing but -1, 0. This is 0, -1. This is 1, 0. This is 0, 1, etc. Right? So it's basically you're saying that this constraint is kind of restricting the region in the parameter space from where your, where your solution may exist. Right? So this parameter space, this constraint simply say that any solution outside this circle or outside this rhombus is not acceptable. Okay? So that is what it's basically this constraint corresponds to. Okay, so now it still doesn't explain that why you are getting the sparse solution in case of this L1 regularization. So we'll come back to that in a second. Let's clean this up. Okay, so all right. So now if you go back to the term that you are trying to minimize, so basically this term. So this term you can think about, in the geometric representation, it kind of looks like a circle or it looks like an ellipse, depending on what the exact values are. So in this picture, what you're showing here is that this region over here is the parameter space where any feasible solution will satisfy this constraint that your square 2 norm is at most, some one or some parameter. Similarly, on the right-hand side figure, this shaded region is the region in the parameter space which satisfies this L1 norm constraint. And this picture over here, it basically shows each of these contours, shows the corresponding values in this parameter space where the objective function that you're trying to minimize has the same values. So the point over here is that where this function value is the minimum, absolute minimum. So as you're going farther away, the objective function value is increasing. So if you keep on increasing these contours, so the first time, so the farther you are from this point, the objective function value is increasing, right? So your goal is to minimize the objective function value, but at the same time, that solution should also lie within this designated area that corresponds to this restriction on this by given by this regularization term. So the moment if you increase this contour such that the objective function values increases, the first time it touches this contour, that is the minimum value that satisfies this constraint. At the same time, your objective function is also made. So same thing happens over here. Now, because of this rhombus region, many of these, so let's say the first time that this contour reaches this, region is a vertex. And because of this, shape of this, see in this case, this vertex has one of the corresponding entries is 0. So see, if this is your W1 coordinate and this is your W2 coordinate, the first time that it satisfies this constraint that the parameter space lies within this, L1 regularized region in the parameter space, and the objective function is minimum. The first time it touches, because if you increase it even further, the objective function value will be even more, so it's not the minimum anymore. Then this vertex has the corresponding W2 values at 0. Right? So that means it has only one parameter said to be non-zero, everything else is 0. So once you go to a higher dimension, meaning that once you have more number of features, then this L1 norm region in the parameter space, it kind of have a kind of a convex shape where you have many vertices of this type or many kind of planes where many of these parameters are 0. And as you are increasing this contour, so that the function value is increasing, but the first time it kind of touches this region where the feasible solutions are allowed, so that the constraint, the regularization constraint is satisfied, then many of these entries will be kind of 0, only few will be non-zero. And that is kind of the justification that why the solution that you get using this L1 norm or L1 regularization gives rise to a non-zero, kind of a very sparse solution of the parameter that you get. Okay, so now, so given a n by m design matrix phi and the corresponding different true levels from your training set, the least square linear regression solution is essentially finds a W, which is a linear combination of the columns of W, right, with coefficients W1, W2. So it is nothing but an orthogonal projection of Y into the space spanned by the column. So think about that there are two different columns, right? So it's, let's say, n cross 2 matrix. So you can represent, and let's say, try to see that what this orthogonal projection actually means. So let's say this is the space spanned by, so let's say your phi is actually, there are two columns, phi 1 and basically phi 2, right? So this is basically the first column. So this is again, n cross 2 matrix. And let's say this is the space spanned by these two columns. So let's say this is the direction where you have phi cross phi 1. And let's say this is the direction which is phi 2. And remember, these two need not be orthogonal to each other. It is simply showing that this is the space spanned by these two vectors. And now let's say you have a y somewhere over here. So this is your y vector. So since your solution is going to be a linear combination of this phi 1 and phi 2, any solution is going to lie within the space spanned by this. Essentially, that means if you make this orthogonal projection onto the space, so that this is basically a right angle vector. So this is the base that you can hope for. that is the closest vector of y that lies onto this space spanned by, so let's call it, phi, I don't know, let's say phi tilde. So this is basically the closest vector of y that lies within the space spanned by phi 1 and phi 2. So the other component of y, so y is these two component, right? So let's call this, y, I don't know, let's say tilde phi, which is orthogonal to this. So that means any y you can write as a sum of the component of y, which basically lies in the space spanned by all these different columns of this design matrix, plus the component which is orthogonal to that, which is represented by this. And there is no way you can kind of compensate for this quantity unless, because you're trying to find a solution in this space. So if y has certain component which is orthogonal to the space spanned by all these different vectors, that is some kind of error that we have to just accept, because the solution that we're looking for cannot represent any vector which is out of an orthogonal space. Okay, so so that means once you choose the different set of columns of your design matrix, the space spanned by those columns basically describes that how well good approximation of y you can have. If the space spanned by all these different vectors happens to have contain this vector y, then you can have a very good kind of representation. But if there is a significant component of y that goes beyond, which is not captured by the space spanned by all the different columns, that means if there is a significant amount which is orthogonal to the space component, space spanned by all these different columns, then there is some error that you have to deal with, accept. You cannot basically, your model cannot, account for that. Okay, anyway, so let me just remove these things. Okay. All right, so the next thing that we wanted to also discuss, one of the points that we raised before, is that what happens if the linear model doesn't pass to the origin, right? Okay, so that means that now we can kind of we can kind of add an offset term W naught, which basically kind of measures how far the linear the model is going from the origin. So because now we have an additional parameter in your sort of W along with this, let's see, along with your D different, along with your, sorry, kind of still not there yet. Okay. Let's see. Oh, actually, this should be. Oops. Maybe. Oops, sorry, this should be WD, and this should be the D features. So along with these D features, also you have another offset parameter. So now essentially I'm looking for D plus 1 parameters. The noise terms is still the same. But we can actually use a simple trick to use the same solution that we have obtained before, and the trick is as follows. So essentially what we do is that we can pad the data point with an extra 1, so that, and then the pad the W vector, W tilde to be, we add this additional bias term at the beginning. So now if you look at that, how that actually affects, if you compute this inner product, between so X tilde inner product with W tilde. So it will nothing but, the first term 1 multiplied by W will give you W, and then second term will be nothing but, Xi Wi, where I goes from 1 to D. So this is nothing but simply W naught plus exact same model that we had before here. So X transpose. Right? So you basically, and then once we have that representation, And now your output level is going to be exactly the same as before. Only difference is that now instead of B features or B covariates, I have B plus 1 covariates, right? And everything else kind of remains the same. So, so that way it's kind of easy to handle this linear model that does not pass through the origin. All right. So one more thing that we want to quickly cover before we stop is that in linear regression model, we are given a training data set that we have said, right? The linear regression model outputs y as a function of xi. So this is an estimate of the output yi, which is a linear function of xi. So you might ask that what happens when a pair x and y is given and a linear regression model is applied to predict this output as y given x. So what is the error or loss, as it is often called in the machine learning literature, we suffer on average, right? So that is, you are given a data point. Based on the data point, you're making a prediction, and then now you're computing, comparing how well does it do the prediction with respect to the actual true output level. And then you're basically asking that, well, it's a random data point, but what happens on average, right? So basically, what is the expected value of your error? So this is pretty much what we want to capture in this, this. So yx in this kind of equation, y of x is your prediction for any given data point x, and then y is the true level, and p, x, and y is the joint distribution of the covariates, features, and the output. So if you simply sample the data point according to this probability distribution, predict for the data point x's level, compute this square difference, then what is the expected error? So that is what we'll be interested in. So our goal is to choose the prediction of x as a function of x, which is y of x, that minimizes this average error. So using simple calculus of variation, if we take the derivative with respect to y, d of y, then we can see that we have the square term, so we have a 2, so it simply become integration of yx minus y, and then p of xy dy, and we want to set it to 0, and then we can simply solve this quantity. So this is kind of easy to work on. This kind of a one-line kind of derivation. Let me quickly walk through it. So 2 actually doesn't matter. So essentially what we are saying here is that if you separate these terms, then we are basically saying, well, y of x and pxy dy minus y p of xy dy. Okay, so now, so if you try to solve for this, okay, so, and you are setting it to 0. So what happens to this first quantity here? So this quantity, if you take it outside, then this quantity p of xy dy, so, and then this quantity simply becomes minus y p of xy dy equal to 0. But this quantity, you are basically taking a joint distribution and integrating over y, or you're marginalizing. So the result is nothing but, let's maybe write down over here. So this is nothing but y times y of x times nothing but the marginal distribution p of x, which is, if you change sides, it's nothing but y times p of xy and then dy. So now if we take px to the bottom, essentially you'll have an expression something like this. So y of x is nothing but y p of xy divided by p of x and then p of y. So p of xy, joint distribution divided by p of x, is nothing but the conditional probability, right? So this is nothing but y of p of y given x and dy. So now this is nothing but the conditional expectation, right? So it is nothing but the exactly a conditional expectation of y given x. Right? So this is kind of a very simple derivation. So essentially, what you have shown is that the solving for yx, when you are trying to minimize this average loss, is nothing but the expected value of y given that x. All right. So let's clean this up. And go to the next point that I'm trying to make. All right. So now, so we can write this yx minus y term that we introduced over here, slightly in a different way by adding and subtracting this term. So it does not change the square at all. But now we can think about that this is a sum of two quantities. So let's call this term, a, this term b. So essentially, you're basically taking a plus b whole square. So you'll have s squared plus b squared plus 2ab terms. Okay. So keep in mind this, and then see how we can kind of expand these two terms. Okay. So this is the first term square plus the second term square plus you have the 2 times the cross product between these two terms. So now to find expected value of this loss, we need to integrate this above equation, remember? So let's focus on the cross product term first. So if you look at this cross product term, you don't need to take the 2 because it's just a constant. So basically you are taking the integration p times xy with respect to dx dy. And then, okay, so this is basically the same thing that we're writing one time. X expected value of y. Yeah. So let's try to write it in a slightly different way. The first term we're keeping it as it is. So the second term, we are kind of writing this p of xy. We are basically first factorizing this joint distribution as a product of p of x times conditional p of y given x. So now once we have factored it in this way, we are now taking only this conditional probability term and then taking this px outside. So now if you compute this inner integral first, so this expected value is kind of a constant term. Now if you take the integration of the second term, this is nothing but y times p of y given x, which is nothing but the conditional expectation. So these two terms become exactly the same. As a result, once you subtract, this is 0. So the cross product terms become 0 in this representation. Okay, so now to make our representations a little bit easier, let's call this conditional expectation as to be a function of x, to be h of x. So that means now we can write this one simply as this yx minus h of x squared plus h of x minus y squared, because we have seen that the cross product terms become 0. So now, so let's separate these out. So the first one is kind of the difference between yx squares and hx, which is basically the true level minus your prediction. No, sorry. So this is not the true level. So this is kind of your conditional expectation. Y of x is your prediction minus h of x is the conditional expectation, and this is the conditional expectation minus the actual true level. Okay. So let's focus on the first term. The prediction of y of x depends on what training data set we use, because if you use a different training set involving, let's say, 100 examples versus 200 examples, or even if the training set size is same, depending on what exact training points are included in that set, we'll have different variations in our solution. So we would better represent this y of x to also include d to represent that it's just a random instantiation of this training set, and that also affects the solution that we get. So the first term essentially will represent as y of x, but will represent d as well to represent that the data set also has some contribution in the solution minus this conditional expectation thing, and then we'll basically take the square of that and then take the expectation with respect to p of x. So now we can write this one again. We can introduce a sort of an expected terms, add and subtract. So this expectation now with respect to the all different random training sets that we can take. Again, we can, if you derive this, is basically that there are two terms, the square of the first terms once you expand the a plus b whole square. So the square of the first term plus square of the second term plus 2 times the cross products. Now, taking expectation with respect to the data sets, if you think about each training data set is kind of random, then the cross product term vanishes, and essentially we are left with the expected value over the training data sets, that your solution that you get minus your conditional expectation square of that, and then you have this variance second term, which is again your solution based on your training data and the x, as well as the expectation with respect to the data set. So the first term you can think about as a variance term, the bias term, and the second term you can think about the variance term. So the bias term basically tells us that how close the output estimation is to the true underlying output, which is the conditional distribution, conditional expectation. And the variance tells us that how reliable our estimation is. That is, if we change a different training set, how much it is going to vary. So when we say that the model is actually overfitted versus underfitted, which is again two common terms in machine learning, is that so I'll come back to this model in a minute. But again, so now if you look at this expected loss, now has 3 different quantities. So one is the bias term, square of this bias term. You have this variance terms and this noise terms. And remember, this noise term simply comes from this fact that, if you go back to the slide, is that whether how your actual output levels compare, how different they are from the conditional expectation, right? And so the way that we basically, this noise term is there is nothing much you can do, because if your true levels are very, the best model that it describes using all this kind of statistical technique is that your conditional expectation is kind of your best kind of model that you can hope for. But if your actual levels are kind of different, then this is kind of noise term that you have to kind of accept it. And then now you have these bias square terms and the variance terms that you have control over, that you can kind of try to minimize both these two terms. But then typically you cannot minimize both at the same time. They have kind of interdependence in the sense that if you try to minimize the bias, then the variance increases. If you tries to increase the variance, the bias increases, etc. So if you think about that, how that is going to happen in linear regression case, remember you're talking about this generalized model where you have the flexibility of choosing different basis functions. So the more expressive basis functions that you can add in your design matrix, your model becomes more and more complex. And then similarly, but then sometimes it can be over complex, and those that might give rise to certain effect on this bias variance trade-off. On the other hand, the other extreme could be that your basis functions could be too simple, that cannot disguise your data. For example, the actual input-output relationship is kind of a nonlinear model where each of these basis functions are a linear function. So then a linear combination of these linear models cannot be, where individual basis functions are linear, may not be a good representation for your nonlinear model, in which case it will kind of underfit. So to represent this kind of, more kind of in a pictorial manner, you can think about that in the x-axis, you're kind of increasing this model complexity. So in the generalized linear regression term, you can think about that the model becomes more and more complex if you add more columns in your design matrix, and individual columns represent, say, a complicated nonlinear function. And y-axis, let's say you are using this prediction error. So typically what happens is that now the whole idea of training is that you want to learn a model, but the goal is that the learned model will also predict well on unseen test examples. So you can measure those sort of using, once you are given finite training and test data set, you can measure the training error and the test error. And let's say this is kind of the plot that, so the blue plot is kind of the prediction error from the training example of the training error, and the red curves is the test sample. So typically in machine learning, you see this kind of model complexity versus error, so which this kind of bias variance trade-off curve. So the model typically is called overfitted when the training error is very small, but the testing error is very large. And this typically happens if you are somewhere on the right side of this curve where your model is so complex that it can fit your training data precisely. That means it kind of remembers your training data points, but it cannot generalize very well. Which is kind of the right side where you have very low bias and the high variance side, in the sense that it kind of fit your training data very well, but if you change things a little bit, then it can, if you're from your training data point, if you change your test data point just a little bit, then it can give a very different result. So the model is typically underfitted when both training error and testing errors are large. So where your pretty high bias, in the sense that if your true model is nonlinear and the model that you are trying to your model, so the actual input-output relationship is a nonlinear and your model is linear, so then the linear model may not be powerful enough to capture the nonlinearity of the actual input-output relationship. In that case, you are going to have a very high bias because your conditional expected values are going to be very different than the true values. And then, but then you are going to have a very low variance. So most of the time you are kind of consistent, but you are doing a consistent bad prediction, right? So both training error and testing error are typically large in this case because the model is not expressive enough to represent the complicated kind of complex relationship, input-output relationship by this model. So these are kind of this. So here the model is not complex enough to capture this information. So this is kind of the bias variance, or typically calls also this U kind of shape, because it's kind of dips this generalization or test error first, and this increases again, is something that you learn in machine learning. However, you have to take this with a grain of salt, because with the advent of deep learning models, and especially with over-parameterized deep learning, where the number of parameters exceeds kind of tremendously, then you also see a slightly different bias variance curves where your test error, training error continuously kind of decreases. Training on the other hand, your test error kind of decreases first, then it increases, then again it kind of decreases. So you kind of see a double descent, or sometimes even multiple descent kind of behavior. And that is something very interesting feature that people are trying to explain. And there are some explanation of that, why this kind of behavior happens in case of more complex models, and under what conditions such this kind of behavior, multiple descent or double descent, happens in the context of deep learning, are kind of understood, but still there are many open questions. But in anyway, so I hope this video will give you a little bit better understanding of what linear regression is. How do you find this closed form solution? And in the closed form solution, if we cannot take this inverse, then how we can sort of do a regularization that corresponds to nothing but making your the matrix for which you have to take the inverse diagonal heavy, and by that making the singular values non-zero, so that you can take the matrix. Also, we talked about how to explain this from the probabilistic viewpoint. We also talked about that when you do the regularization point of view, how a L1 non-penalty or L1 regularization gives rise to a sparse solution, and so on. Anyway, so hopefully this video will explain some of these very basic fundamental properties of linear regression, and hopefully it will help you to understand linear regression.